ever wanted to control all devices surrounding you just by your task? Well, Mint Automation Home is the perfect solution for you. This Android app lets users control all wirelessly connected devices just by the task based on their EEG signal patterns. This app will not just hugely benefit paralyzed and disabled people, but also make our lives much more convenient and exciting. For this automation home project, Mint was divided into mainly 3 sub-teams: the app, the signal processing, and the machine learning team.
Our Android application implements a selection of devices and actions controllable by Google Home, for example, managing smart lights and playing music. A command is sent from the machine learning team, which would then control the application to automatically select one of those actions, then initiate Android's text-to-speech and voice capabilities to communicate with the Google Home. Without any physical interaction, the goal is for the end user to effortlessly use the application as a way to control a variety of Google Home actions.
Our Android app is developed in Java on Android Studio, and our choice of design was Material UI. Our app can activate your Google Home in 2 ways: thinking and physical touch. You can add your Bluetooth devices through our Bluetooth page shown over here. These 4 boxes represent a different type of command. Each command can be edited by tapping on one of these boxes. You can add a nickname for the command or change the type of the command. You can activate these commands by simply tapping on this play button. Or you could use a headset and think to trigger various types of commands. Make sure to save your changes to trigger your new commands. Our goal is to allow users to connect to any Bluetooth devices and control them just by thinking, but for our submission, we have focused on the Google Home device. You can add any Bluetooth device through our Bluetooth page and edit the nickname and type of commands in the main homepage. After editing the type of commands, our machine learning model will then read from the EEG headset through a Wi-Fi shield and classify the thoughts into 1, 2, 3, or 4, which represents raising your left arm, your left leg, your right arm, and your right leg. Each of these thoughts will trigger the following 4 box commands, respectively.
As the signal processing team, our job begins with the OpenBCI EEG system, and it ends with a filtered signal ready to be sent to the machine learning team for classification. To begin this process, we had to determine what signal to search for, and our research led us to look for the motor imagery signals which elicited during both imagined and actual movement of the limbs. To reduce the large noise-to-signal ratio in our EEG data, our first step was to implement a bandpass filter. Motor imagery signals are known to be elicited between 8 and 30 Hz, and so that's where we set the cutoffs. We then tried different techniques such as independent component analysis, but none of these were sufficient. Currently, we're using common spatial patterns and hoping that will provide better results.
All of our data was collected through the OpenBCI Cyton board. We created a video for the users to follow along, which would prompt them to move either one of their limbs. And from this, we were able to create a log file, which helped us correspond the data to the actual log file, so you can know when the users are moving each one of their limbs.
So we use machine learning fundamentally for classification. We want to train a computer to recognize different kinds of EEG signals and to classify them into corresponding actions that can then be carried out. So the way we collect our training data is we hook up a user to an EEG and we tell them to either raise their left arm, left leg, or right leg. And those theoretically generate different kinds of brain waves that can be produced, picked up by our apparatus, and sent to our model for training. So the biggest challenge we have by far is a limited supply of training data because of how time-consuming it is to actually hook someone up to the apparatus and collect this training data. However, despite it not being as much data as we would all like, we still have enough data to train on, and we think the results we've achieved training on this limited data is very respectable, and it proves the concept of machine learning and how effective it is. And there's a lot of potential moving forward with more data and better development of our model. So now other members of the machine learning team will talk about the specifics of the model and how we've managed to build it.
The data initially comes to us in the form of a live voltage stream in 1-second snippets from 8 different channels. Each channel's wavelet gets then converted into a 12 by 12 spectrogram so that the input event is a 12 by 12 by 8 tensor. We're working with about 550 events, half of which are null, and then the other half is evenly distributed among the 4 signals. Working with limited data can be a challenge because it can easily lead to overfitting. What we've done to approach this challenge is incorporate dropout layers into our network. What this does is while training, it randomly sets hidden layer neurons to 0. This prevents over-reliance on certain neurons and prevents overtraining. We're also still developing new ways to pre-process the data, as there's no reason to believe that the current spectrogram-based approach is the best way to do it. The data initially comes to us in the form of a live voltage stream in 1-second snippets from 8 different channels. Each channel's wavelet gets then converted into a 12 by 12 spectrogram so that the input event is a 12 by 12 by 8 tensor. We're working with about 550 events, half of which are null, and then the other half is evenly distributed among the 4 signals. Working with limited data can be a challenge because it can easily lead to overfitting. What we've done to approach this challenge is incorporate dropout layers into our network. What this does is while training, it randomly sets hidden layer neurons to 0. This prevents over-reliance on certain neurons and prevents overtraining. We're also still developing new ways to pre-process the data, as there's no reason to believe that the current spectrogram-based approach is the best way to do it.
In the actual implementation, the application will use a trained model that samples continuously in 1-second intervals. When the network predicts that the user has performed an action, then a message will be sent to the app so it can carry out the appropriate task. The data is compiled into a filtered string and then sent to the mobile app via Bluetooth. A challenge we faced while training the machine learning model was gathering enough training data, since we found that existing datasets were not compatible with our customized EEG headset.
To summarize our efforts, we looked into models that took both time-based inputs, which were filtered voltage values, and models that took in frequency-based inputs, which were the same voltage values passed through a frequency spectrogram. So the final machine learning model that we ended up using was a simple CNN for a spectrogram input, which outperformed our time series model, which was based on the paper Deep Learning for EEG Motor Imagery Classification based on multi-layer CNN's feature fusion by Amine al. 2019. The results for both models ended up being quite similar for our data, but the CNN was much more lightweight and faster to perform inference on, so we ended up going with that. We also attempted to aid in the lack of data by using pre-training on a publicly available dataset that was called a large electroencephalographic motor imagery dataset for electroencephalographic brain-computer interfaces, which contained very similar classes to our data. Pre-training is a commonly used technique in machine learning to obtain a reasonable starting point for a model, which is particularly important when you have smaller datasets. And as mentioned before, a major challenge that we faced, which was particularly difficult to remedy, especially during the difficult environment that our team currently operates under, was the lack of data. Despite pre-training and fine-tuning, the amount of data we recorded was pretty much not sufficient to help the model learn the complex features that we tend to find in EEG data. So going on, we expect to increase the amount of data collected significantly, and our reasonable performance on the pre-training dataset shows that success is possible.